I gave you an example of application of the linear systems, right, before. So you remember I have shown an example how you can introduce the model of money, right? So essentially. So essentially, if you have just natural exchange in your society, so how you can introduce money, which is convenient universal good. So I did it before. So and I told you already that a guy who invented this kind of stuff, so essentially got Nobel Prize for that in economics. So now about application of all these bases and so on. So for example, let us consider equation like that. So second derivative of y equals to let me make it a little bit more complex. Let's say, yeah, plus y prime plus y equals to 0. So this is second derivative, this is first derivative. So this is what is called ordinary differential equation of the second order. What is important, this is linear second order ODE. Why? Because you can represent it as d2 by dx squared plus d by dx plus 1. And you can call this operator L applied to y equals to 0. So let us consider space of twice continuously differentiable functions on the interval from a to b. So x belongs to the interval from a to b. Let's say from 0 to 10. So why I need these twice continuously differentiable functions? Because I need to be able to apply this second derivative to the function. So you can easily show that this is a vector space. So vector space of twice continuously differentiable functions. Okay, on the interval from 0 to 10. So now, okay, how you can solve it? So you can try to look for a solution in the form, so some constant a multiplied by e to the power lambda x. So if you substitute this here, or let's say here, yeah, by the way, L is linear operator. Why? Because differentiation is a linear operator. So we have seen this already. So essentially, you can check that it starts from the vector space of these functions and ends in the vector space of continuous functions on the same interval. Why? Because we consider y's belonging to the vector space of twice continuously differentiable function. It means that second derivative exists and continues, right? So then if you apply this, if you consider this, so this is continuous because we start from here. So y belongs to that. So first derivative obviously also continuous, and y itself is continuous. So sum of continuous functions gives you a continuous function. So essentially you can say that this L maps C2 0 10 to C continuous functions on the interval from 0 to 10. Okay, now how can we solve it? Let us try to consider this. So if I will substitute it here, I will get a lambda squared here, this one, second derivative, e lambda x plus a lambda e lambda x. So I applied the first derivative here, plus a e lambda x equals to 0. So I substituted that. Okay, a in general is an arbitrary constant. So let me get rid of it. E to the power lambda x is a non-zero scalar. I can also divide by that. So as a result, I'm getting lambda squared plus lambda plus 1 equals to 0. So, okay, I can solve this quadratic equation for lambda. Lambda 1, 2 equals to plus minus 1. Minus 1. Minus 1, so minus this 1 here, plus minus square root of 1 minus 4. You know, for simplicity, let us make it like that with negative sign, so that we would stay in real numbers divided by 2. So as a result, it's negative 1/2 plus minus square root of 5. Okay, so I know that C1 e to the power negative 1/2 plus square root of 5 multiplied by x is a solution. And also C2, so I use this just a constant, right? So I can call it C2, for example. E to the power negative 1/2 negative square root of 5 x is also a solution. So C1, C2 are constants. Okay, these and these are solutions. Okay, I can show, it's easy to show that these two functions are linearly independent. How can you do this? Just using the following trick. So alpha 1, just as usual. So what we need to show that minus 1/2 plus square root of 5x plus alpha 2 e minus 1/2 minus square root of 5x equals to 0. So we need to show that the only possibility for this to be, for this to be true is when alpha 1 and alpha 2 are equal to 0. Okay, but one equation is not enough. So what can I do? If this is true, so then I can differentiate it, and I will get that this and this also has to be equal to 0. Now I can just write e, okay, I will call it lambda 1x. Here will be lambda 1 e lambda 1x. Here will be e to the power lambda 2x. And here will be lambda 2 e to the power lambda 2x multiplied by alpha 1 alpha 2 equals to 0. So for every point X, this has to be true. So this has to be true, right? For every X. And from the other point of view, I can just try to solve it. So to figure out what will be the condition for this equation, system of linear equations to be solvable, and we had it. So we need to prove that this is non-singular matrix. So you had a problem in your homework that A, B, C, D is non-singular if AD minus CB is not equal to 0. So you have this problem in your homework. Okay, so let me check it. So lambda 2 e to the power lambda 1 plus lambda 2 x minus lambda 1 e to the power lambda 1 plus lambda 2 x equals to 0. So I can just write lambda 1, lambda 2 minus lambda 1 e to the power lambda 1 plus lambda 2 x equals to 0. So this is not equal to 0, and this is not equal to 0. So you can check it. So you will see that lambda 1 is not equal. Lambda 1 is not equal to lambda 2 because lambda 1 is with positive sign, this with negative sign. So they are two different numbers. Okay, we see that this is non-singular. So from here, it follows immediately that this homogeneous system of linear equations has a unique solution, and this unique solution is a trivial solution. So we have proven that these solutions are linearly independent. So, okay, we have found that for the space of solutions, or in other words, null space of this operator L, so what we have shown? We have shown that null space of L, which is d2 by dx squared plus d by dx plus 1, minus 1, sorry, we replace it with minus 1. So will be space of solutions. So have a look. Null space of a linear operator so constitutes all possible y's to which you can apply your linear operator, and it will give you 0 vector. Okay, so we have proven that null space is a vector space, right? So because it's subspace of the original vector space. So then have a look. So your solution, when you will be integrating this equation, so your solution, so how many, so essentially when you integrate once, so you, because here you have two second derivatives, so you need to integrate twice in order to solve it, right? When you integrate once, what you are getting? You're getting one integration constant. When you integrate twice, you're getting two integration constants, right? Two integration constants means that two integration constants means that space of solutions is two-dimensional. Why two-dimensional? Because after you integrate twice, you're getting two constants, right? So it means that it will be spanned by some two vectors which are multiplied by these two constants. From the other point of view, right here, we found two solutions, right? Two of them, two solutions. And these two solutions are linearly independent. So we found two vectors in the space of solutions, and these two vectors are linearly independent. And also we know that space of solutions is two-dimensional. So from here, it follows that E lambda 1x, E lambda 2x, they form a basis for the space of solutions. Or it's null space of linear operator L. Okay, so, but because we found the basis for the space of solutions, we know that any solution y of x can be represented as a linear combination of vectors of the basis. Just this. Or if you remember, -1/2 plus square root of 5x plus c2 e -1/2 plus square root of 5 minus, sorry. So we know that general, so-called general solution or arbitrary solution can be represented in this form as linear combination of two solutions which we were able to find. Okay, wonderful. Now let us suppose that at x equal to 0, our y is equal to 5. So this is so-called initial condition. Then and y prime is equal to 1. So then what it means? It means that I can write that at x equal to 0, I substitute just here x equal to 0. I'm getting c1 plus c2 equals to 5. Now I need to compute y prime of x, which will be c1 -1/2 plus square root of 5 e to the power -1/2 plus square root of 5x plus c2 -1/2 minus square root of 5 e to the power -1/2 minus square root of 5x. So this is the derivative. So I substitute x equal to 0 here, and it has to be equal to 1. So I'm getting c1 -1/2 plus square root of 5 plus c2 -1/2 minus square root of 5 equals to 1. This is just a system of two equations for two unknowns. I can solve it, and it will give me the unique solution. So I will determine these two unknowns, and it will give me a unique solution for my ordinary differential equation of the second order. So you see here, so those of you who took this ODE class, so usually in undergraduate ODE class, we just teach how to do this. We do not explain why this is true, why it works. So ODE class is practically, it's almost like calculus, where in calculus you're just given the tools, and you are told that, okay, in this case, use these two. In this case, use these two, but you don't know why they work in most of the cases. So because this is what is proven in so-called mathematical analysis. So it's 401 or 402 courses. So here, so really the whole theory of linear ordinary differential equations is a theory of linear operators. So if you need to solve so-called homogeneous ordinary differential equation, so what we do, we are trying to find the solutions, two linearly independent solutions, and then because this is second order equation, we know that space of solutions is two-dimensional, and we find these two solutions. We show that they are linearly independent, and I will prove, by the way, later that they are linearly independent if lambdas are different. So I will prove that in such a case, solutions for any homomorphism, so solutions will be linearly independent. So I will prove it. So then essentially what I'm doing, so I'm just trying to find solution in some form. Here it is. I'm just looking for a solution in this form. I'm finding two different solutions. I can show, using the knowledge which we have already about homogeneous system, that these two solutions are linearly independent. We have two elements in the vector space of solutions. We know that it's two-dimensional, and we know that these two elements are linearly independent. It means that they will form a basis. So as a result, what can I do? I can say that my arbitrary element of this vector space of solutions can be expressed as a linear combination of vectors of the basis. So after that, I know the so-called general solution of ODE, my ODE. General solution means all possible solutions. Now, if I introduce so-called initial conditions, so this is what is called Cauchy problem for the ODE. So when you introduce initial condition and you want to find solution at any x, any value of x. So then you just write again system of linear equations for these unknowns, C1, C2, which you can resolve. And after that, you know unique solution. That's it. Another application is the following. Let us suppose that you have some data set. So it consists of x and y's on the plane. So for example, here you have this point, this point, this point, and this point, 4 points. Let's say 1, 2, 1.5, 3 at x equal to 3. So it's 1, 2, 3. You have, let's say, 2, and at x equal to 4, you have again 1. For example. Now, you know that these points are really just sampling points from some function, which goes like that. You can say the following. Suppose my f of x is nothing else but polynomial of the third degree, a3x cubed plus a2x squared e1x plus a0. Then what you can do? You can just write it as A3. For example, you substitute first this x and y, right? So you substitute x equal to 1, you're getting A3 plus A2 plus A1 plus A0 equals to 1, right? Okay, now A3 multiplied by 2 cube. So now let us substitute x equal to 2 plus A2 multiplied by 2 squared plus A1 multiplied by 2 plus A0 equals to 1.5, right? This value. Okay, A3 multiplied by 3 cube plus A2 multiplied by 3 squared plus A1 multiplied by 3 plus A0 equals to, here it is, 2. And finally, for the last point, for x equal to 4, A3 multiplied by 4 cubed plus A2 multiplied by 4 squared plus A1 multiplied by 4 plus A0 equals to 1. So this is system of linear equations. Okay, so what I did, I essentially supposed that my function is a polynomial, or I can just consider, so I have 4 points, right? I can consider bases in the space of functions consisting of 4 linearly independent vectors, any linearly independent vectors. So when you consider polynomials, it's just convenient because these vectors are easy to compute and easy to introduce. So this is why polynomial interpolation is so-called polynomial interpolation is so popular. So essentially, you can write it like that, right? After that, this is a linear system of linear equations. 1, 2 cube, 3 cube, 4 cube, 1, 2 square, 3 square, 4 square, 1, 2, 3, 4, 1, 1, 1, 1, multiplied by A3, A2, A1, A0 equals to 1, 1.5, 2, 1. So this is a system of linear equations, which you can solve. And so you essentially considered a vector space of functions, which can go through these 4 points. So you considered 4 basis vectors. In this particular case, x cubed, x2, x, and 1, right? And you found just, you have written this system, so you required this function to go through every point in my data set. And then you wrote system of linear equations. So this is, by the way, called Vandermonde matrix. And you found corresponding coordinates in this particular basis of your function. So you can, for example, consider these bases, x cubed, x squared, x, and 1. Or you can consider different bases, 1, x minus 1, x minus 1, x minus 2, x minus 1, x minus 2, x minus 3. You can show that this is also a basis, so that they are linearly independent. And then what you can do, you can just consider now, so x equal to 1, the first data point. You will see that, so you will be considering your function in the following way. Okay, let me call it C1 multiplied by 1 plus C2 multiplied by x minus 1 plus C3 multiplied by x minus 1 minus 2.
Professor,
Plus,
does this does this basis have to do with the graph that you just showed us?
Yeah. So essentially, I said that I can consider these bases, right? X cubed, x squared, x, and 1, right? And I found the polynomial interpolation. So I found the function which has this form, right? And which goes through all these 4 points, right? Essentially. Is it clear or not?
Yeah, that's clear. I just don't quite understand where you're getting like minus 1.
Have a look. I don't have to consider necessarily the as basis functions, basis of monomials, right? So I don't necessarily need to consider natural basis in the space of polynomials of degree 3, right? I can consider any other four linearly independent vectors, right, in the space of polynomials. Is it clear or not?
Sort of. So you're able just to take any.
So I'm saying
basis.
That, yeah. You see, because if I consider, if I want to represent my function as a polynomial, right, which goes through all these 4 points, it doesn't matter what basis I will use. It will just change the coefficients. So here coefficients will be different, not the same as in this case, but you know that yes, representation with respect to the basis is unique, but it's the same vector, it's the same polynomial. If you will multiply everything in these brackets, so in the end, you will get exactly the same polynomial, right?
Okay, so it's just like a different way of writing the same
different
thing.
Different basis, right?
Different basis, but same polynomial.
Yeah, in the end, it will be the same polynomial. Just have a look what will happen. So here I used x1, right? Here I used x1 and x2. Here I used x1, x2, and x3, right? So pay attention, x1, x2, x3, x4, right? So I used points which I have, right? Sampling points, right? Now have a look what happens. If I consider x equal to 1, if I will substitute it here in my function, what I will get? Because all terms contain x minus 1, all other terms, right? But this one. So they will all be 0. So what I'm getting C1 multiplied by 1 equals to y1, which is in this particular case is 1, right? So one. Now the next sampling point. So C1, if I substitute x equal to 2 here in this f of x, so these two terms will not be 0 or not necessarily be zeros, but this term and this term will be zeros, right? Because of corresponding brackets x minus 2. So I'm getting C1 multiplied by 1 plus C2 multiplied by x equals to 2 minus 1 equals to, have a look at this data set, y2 is equal to 1.5. 1.5. X equal to 3 will give me C1 multiplied by 1 plus C2 multiplied by 3 minus 1 plus, now this term will be 0 because of this bracket, but all other terms will not be zeros. 3 minus 2. And I remember that it has to be equal to 2. And the last one, and it has to be equal to 1 because my data set has 1 here, 1.5 here, 2, 1, right? Okay. So, but from here you can immediately see. So first of all, you can see that this is a lower triangular matrix. So from here you can immediately find that C1 is equal to 1, right? You can substitute it here. So you're just performing forward substitution. You substitute it here, and you can immediately find C2. Now you know C1 and C2, you can immediately find C3. And knowing C1, C2, and C3, you can immediately find C4. So you see, you consider just different bases, and it's very easy to find corresponding coefficients in this representation as a polynomial. This is called Newton's basis, or Newton's approach to polynomial interpolation. So it doesn't matter what basis you use, you know that in the end you will get exactly the same function because you have 4 unknowns, right? So just in the space of polynomials of the third degree, and you can see that this will be cubic polynomial, quadratic, linear, zeroth order, right? So it's just the different bases in the space of polynomials. That's it. So no problem. And but just you consider different bases, and you are getting different coefficients at these different bases. But it's way easier to solve. And even more, what is important that if you add an extra point, for example, if you decide to do for something x equal to 5, you will get extra vector in the basis, but all the coefficients will stay the same. So just you will get extra equation for the extra coefficients, which is convenient. So you are not losing any information. Even more, I can tell you that you can write a basis where you don't need to solve anything. It's called Lagrange basis for polynomial interpolation. And there you know coefficients right away. So you see all these stuff concerning the vector spaces. For example, it's just an example. Vector space of polynomials, or just vector spaces, bases in the vector spaces, linear transformations or homomorphisms, right? Like in this particular case, in the case of ODE, right? So this linear independence, concept of a basis, and so on. So it's all used in other branches of math. I couldn't even call them other branches of math. It's just application of linear algebra. So practically always when there is a simple way or just general way of solution of the problem, so almost always it means that you're working with so-called linear transformation there or something like that. Why? Because there you can use all the power of linear algebra. All these concepts of basis and so on and so on. For example, it's not necessarily to interpolate the function, just represent the function in the basis of polynomials. For example, you can consider the following basis. If we consider x belonging to 0 to pi, so, and we want to consider a space of 2 pi periodic functions. Cosine 2x sine 2x, cosine 3x, sine 3x, and so on. So then you can show that all these functions are linearly independent. They are obviously 2π periodic, right? So, and you can show that they form a basis, essentially. The only problem is that you need to cut it somewhere to make this basis finite dimensional. So, and this is usually the case because if you have, for example, okay, so essentially, if you write sound amplitude as a function of time, you want to you may want to represent it as a sum of sines and cosines, essentially. And you can show that sines and cosines are linearly independent and they form a basis, essentially. And then this is nothing else but Fourier transformation. So when you represent your y of t, your amplitude, as let's say C naught, or let's say A naught multiplied by 1 plus A1 multiplied by cosine of x plus B1 multiplied by sine of x plus A2 multiplied by cosine of 2x plus B2 multiplied by sine of 2x plus and so on. So, and this is essentially nothing else but base of all digital sound processing. So why digital? Because then after you transformed it into these coefficients, A naught, A1, B1, A2, B2, and so on, the Fourier coefficients. So you're working just with these numbers. And you can essentially consider all this inside of the processor. So the ideal amplifier, for example, sound amplifier, or let's say any ideal sound device, you want it to be linear. Why? Because linear, so the device which performs linear transformation of the input sound to output sound, for example, ideal amplifier just multiplies the incoming signal by some coefficient. So increases the amplitude. So increases the amplitude like that. So why it's good? Because if you just perform linear transformation, then you are not generating any new basis vectors. So essentially, you are just changing these coefficients by a little bit. But basis vectors will stay the same. You are not generating new frequencies, not generating distortion. Or in some cases, you want this distortion generation. For example, all these so-called distortion devices for which gives your electric guitar this wonderful sound. So rock guitar so gives this wonderful sound. So why they are doing this? Because they are nonlinear inside. Nonlinear means that they produce new frequencies and produce this sound like that. So practically everything what you are using, so most of the analysis which we can perform and get really good results, so can perform analytically or just even on the computer. So in many cases, so this analysis is using either linear approximation when you just consider that nonlinear contribution in your process is small, and you can take it into account later by perturbations, so-called perturbation theory, but you're just considering it first as linear. As a result, why it's important, it's you can use all the power of linear algebra, all these basis concepts, or all these linear transformation proves that zero transformed into zero, that if you so that basis representation is unique, and so on and so on. And just in few lectures, I will show you that what you can do. You can represent your any linear transformation, any homomorphism, you can represent as a matrix with respect to some basis. Okay, so I have a few minutes left. Yeah, by the way, so I forgot to say it in the beginning of the lecture. So by request, I extended the homework till midnight. So if you want to add something to your homework or correct it, so you can do this till the midnight, because multiple submissions are allowed. Okay, so I have a few minutes left, 7 minutes. So I want to prove a lemma, or just, yeah, so I will formulate it and then we'll explain what it means and then we'll prove it. So lemma. So for any homomorphism, the inverse image of a subspace of the range is a subspace of the domain. In particular, the inverse image of the trivial subspace is the range of the trivial subspace of the range, sorry, is a subspace of the domain. Okay, first let me explain what it means. So we start, so let us suppose that we have homomorphism from V, vector space V, to vector space W. For example, from the vector space of twice continuously differentiable functions to the vector space of continuous functions on the interval. So it means that we start from here, and for every point, we are producing another point in V. So this is domain. So essentially where our homomorphism is defined, and this is codomain. So the vector space where results of this transformation belongs. So what is a range? A range, it means that you have to apply this homomorphism to all possible vectors in V, and as a result, you will get some subspace of W. So this is range of H. So all possible results of application of our homomorphism H to all vectors in V. So you produce this. So then And before we have shown that range is a subspace of W. Now, the question is, so the statement of the lemma is that for any homomorphism, the inverse image of a subspace of the range is a subspace. It means that if I will consider some subspace of the range here, subspace, so this is range. So this is subspace of the range. And I will consider inverse image. What does it mean? It means that all possible elements of my domain, if I apply homomorphism to them, so they will give me this subspace in the range. Or inverse image means that if I will just consider inverse function like that. So the statement is that this also a subspace of my vector space V. So, for example, if I will consider just zero vector in W, we know that all subspaces contain a zero vector, right? So then all possible elements which are mapped to the zero vector in W will also form a subspace. And this is nothing else but so-called null space or kernel of H. So is it clear? Is it clear? So what does it mean? What the statement of the lemma means? So for any homomorphism, the inverse image of any subspace of the range, so you consider range, right? All possible outcomes of the homomorphism applied to the vector space V, right? So this is essentially H of V, the range of the homomorphism. So, but then you consider this subspace of the range, and then the statement is that inverse image, so all possible vectors, homomorphism of which gives me this subspace, so also will form a subspace in the original domain. And even more, if I will consider the trivial subspace, which means subspace containing just zero vector, so the set of all elements of my vector space V, which are mapped to the zero vector, pay attention, in general, this is not just zero vector. We know that zero vector of V is mapped to the zero vector of W, right? But this is not isomorphism anymore. It can be many vectors which are mapped to the zero vector, right? So the statement is that this set of all possible vectors which are mapped to the zero vector in W, in the codomain, is also forming a subspace. And this set is called null space or kernel of the homomorphism. So is it clear or not? I will prove this lemma on the next lecture, but is it clear or not what I'm trying to tell?
Yeah, that makes sense.
Okay, perfect.